Welcome to our review on calculating energy changes. The first thing we need to know then is what the phrase bond energy actually means. So anytime we talk about a bond energy, we're referring to the amount of energy that we need to break 1 mole of a particular bond, and it's measured in the units kilojoules per mole. So the table in the bottom left there just gives you a selection of different bonds and the amount of energy that's required to break 1 mole of them. So at the top there we've got the carbon-carbon bond, which is a single covalent bond, as you can see, and that needs 347 kilojoules per mole. If you go down to the line second from bottom, you can see we've got the double carbon-carbon bond, which needs 612 kilojoules per mole. So that when we go from a single bond to a double bond to a triple bond, the amount of energy needed to break them will increase. And you can hopefully see in the table there as well that when different atoms are joined through a bond, then the energy required to separate them also changes. So different bonds have different bond energies. Whenever you're given a table of our bond energies like this, they're using mean bond energies. So that if we did an experiment and then we actually recorded the values, they would be different to the mean ones. So we can actually use these bond energies to calculate energy changes in a reaction. So in order to do that, we need to use two things: the energy transferred to break the bonds in our reactants and the energy transferred when new bonds are made in the products. So we could get a question like the one here: calculate the energy change when ethene burns completely in oxygen. So in that grey box, what we've actually got are displayed formulas for all of the different compounds involved. So the first thing that we're going to do is write down the number of bond of each type in the reactants. So what we can hopefully see in there, in our first compound, which is our ethene, then we've got one double carbon-carbon bond in the centre there. Then we've got 4 carbon-hydrogen bonds coming out from, obviously, the 4 corners. And we've got 3 double oxygen-oxygen bonds. So those are our total bonds for our reactants. The second thing to do is we use the table of information, because they will always give you a table. Don't worry, you don't have to memorize all those bond energies. So you use the table of information to substitute in the bond energies for each type. So our carbon-carbon bond, that was a double bond at the beginning, then that's 612. So 1 times 612 plus our 4 times 413 for our carbon-hydrogen bonds, plus 3 times 498, our double oxygen-oxygen bond. So when you work that out, it gives you 3,758 kilojoules per mole, which is the total energy transferred to break all the bonds. Then we can do the same thing with our products. So the first thing we're going to do is write down the number of each bond type in our products. So if we have a look at our equation, what we can see is that in carbon dioxide we have 2 double carbon-oxygen bonds, and then we've got 2 molecules of that. So overall we've got 4 double carbon-oxygen bonds. Then we've got 4 hydrogen-oxygen bonds as well. So once more we substitute in from the table we'll be given in our question the actual bond energies for each, and then work out the total energy transferred when all those bonds are made. And in this case we end up with 5,076 kilojoules per mole. So the last thing we then need to do is calculate the energy change, and we do that by having our energy transferred to break the bonds minus the energy transferred to make the bonds. So in our question that was 3,758 minus 5,076, which gives us an energy change of minus 1,318 kilojoules per mole. Make sure that you write down the sign, whether it's positive or negative, to represent the energy change. And make sure that you do have the energy transferred to break the bonds first in your actual calculation. So what do those positive and negative signs actually tell us in the energy change? Well, if we have a negative sign, then that tells us that our reaction is exothermic. Whereas if we have a positive sign, then we have an endothermic reaction. So what we can actually do is, by carrying out that calculation, we can then identify whether the reaction is endothermic or exothermic just by looking at the sign of our answer.